and from TU Vienna. Thank you. Oh.
So those of you who don't have about an hour, this kind of guest network. Sorry for that.
So let me introduce Sandra Müller. The first speaker is Sandra Müller from TU Vienna. Thank you.
Well, thanks, Grieger. Well, I mean, I feel pleased to have such a chair that knows the topic so well. I mean, how else can you introduce me? Yeah? Okay, so I will talk about determinacy and generic absoluteness for the definable power set of the universally Baire sets. And of course, I will introduce all the topic, I mean, sort of every word that's in the title, and then we will be halfway through the talk. And then I will start with some motivation, okay? Let me actually try. I mean, I will try to step on the stairs and hope to not fall down. Okay, let's see. So what is the motivation? So if we study models of determinacy, so I mean models where if you consider two-player games on the natural numbers of length omega, one of the two players has a winning strategy, then you can use them for many things, but we can, in particular, for example, use them as ground models to force over. And there are some very nice examples that showed up recently. So, I mean, Wooden developed his axiom star. That's a forcing axiom, even for forcing over models of determinacy in some sense. And Aspero and Ralph Schindler proved recently that you can connect this kind of forcing axiom to the standard forcing axioms. I mean, they proved that MM++ implies star. And Wooden forced this forcing axiom MM++ for size continuum over a model of ADR plus theta is regular, so that's a strong model of determinacy. Then recently, Paul Larsen and Gregor Sargsyan forced even more over an even stronger model of determinacy. And the question is if it's possible to construct such strong models of determinacy just from large cardinals without assuming any further assumptions. Because the model they constructed to force, I mean, if you know what it is, I mean, to force, for example, the failure of the KC iterability conjecture in some sense, or just to force this failure of squares, that used very heavy inner model theoretic machinery. So, I mean, they used a hot mouse, yeah? Whatever, I mean, I will not talk about hot mice for the rest of the talk, but, you know, to construct this, you need a lot of inner model theory and machinery. So, again, the question is, I mean, can we do it, for example, from less machinery? Or to make the question more precise, I mean, what kind of strong models of determinacy can we construct? So what kind of nice subsets of the universally Baire sets can we add to the model L gamma infinity R? Okay, so for the rest of the talk, I mean, we will step back and I will introduce what these things mean, okay? So the outline, I mean, first I will tell you what universally Baire sets are and why we care about them. Then I will tell you what generic absoluteness is and why we care about it. And then I will define the UB power set, which is the result that we can sort of add all of these things to the model and still have a model of determinacy and even more. And I mean, Grieger already mentioned, I mean, all of what I will talk about, I mean, especially this part, I mean, this is sort of folklore. I mean, this part is joined with Gregor Sargsyan. So the main result is that we will end up getting determinacy and generic absoluteness, what's called ceiling, for the UB power set of the universally Baire sets. Okay, let's start slow and let's look at universally Baire sets. So the definition of universally Baire sets actually comes from topology. So it's roughly due to Schillinger-Ward and was formalized by Fang, Magido, and Wooden. And they defined that a subset A of a topological space is universally Baire if for every topological space X and continuous embedding f from X to Y, pre-image has the property of Baire. Okay, so there are lots of examples of sets that are universally Baire. For example, every open set is universally Baire, I mean in Baire space with the standard topology. Then every Borel set is universally Baire. You can even prove every analytic set is universally Baire. But I mean, okay, I mean, then that somehow stops. And in fact, this is not the definition we want to use. Yeah? I mean, I put it because I've heard that a lot of you are working on like set theoretic topology, so you might like this one. Let me show you the one that is more useful for set theory. Yeah, that turns out to be equivalent, and this is what Fang, Magido, and Wooden actually proved. But the examples, of course, stay the same. Yeah, so we keep the examples. And what we, in some sense, want to do we want to find examples that are more complicated than these. Okay, so the definition that we want to use starts from the concept of a Suslin set. So being Suslin is a generalization of being analytic. And more precisely, a set of reals is Suslin if it's the projection of a tree, but not a tree on just omega, a tree on omega times kappa for some ordinal kappa. Okay, let me give you a picture. If I say tree, then what I mean is something like this. So we have a tree of height omega, and it has some branches, for example. The nodes of the tree are of the form n comma alpha. Yeah, so the first coordinate is a natural number, and the second coordinate can be some ordinal. I mean, in this case, an ordinal less than kappa. And we look at the set of branches through the tree. So branches are just these infinite chains sort of that go all the way up to omega. And we say that some real x is in the projection of the tree, of the set of branches formally. Well, if it's an infinite sequence, and 0, and 1, and 2, and so forth, and there is a branch such that these n's are always the first coordinates of elements of the branch. And then we can say that a set of reals, or I mean, when I say reals, I actually mean elements of Baire or subsets of Baire space, is Suslin if it's the projection of some such tree. Okay? And now we can use this concept and define when something is a universally Baire set by saying that it's even nicer. I mean, it's not only the projection of a tree, it's the projection of a very nice tree, and actually sort of a nice complementing pair of trees. So let's take some set. Again, a set of reals. So we have our set theoretic universe here, and we take some set of reals A. Well, then we say this is universally Baire if we can somehow canonically extend it to larger universes. So again, I mean, I will define with a picture, and then I will give you the formal definition afterwards. So we take our universe V, and we look at extensions. I mean, formally, what we want to look at are forcing extensions, V of G. If you don't know what that is, just think of some canonical expansion. Yeah, we make the universe wider, we add more reals. We still have our set A, but now the question is, what do we do with the new reals? Yeah, we have a wider universe, so we need to do something with the reals that we added. I mean, the question is, should they belong to the set A or not in this extension? And well, what we want is a canonical answer to this question. And there is actually such a canonical expansion if the set A is given by a nice pair of trees. So what do I mean by this? So let's suppose the set A is a Suslin set. So A is the projection of some tree. And at the same time, the complement of A is also the projection of a tree. Yeah, so that's the green part, the complement of A in the reals. And let's suppose the trees are so nice that they're not only complementing each other here in V, but they remain complementing each other in this generic extension, V of G. So if this is the case, then we can just define the expansion of A to be the projection of the same tree T. Yeah, and we will remain the property that they're complementing each other. So the green part is the projection of S, and the orange one is the projection of T in the generic extension. And this canonically defines as some kind of expansion of the set A. And it turns out that this is independent of the choice of the trees and so forth. Yeah. So if we assume that the trees are sufficiently nice and they remain complementing in the generic extensions, then this gives us a canonical notion of expanding the set A. And if we can do this, we call the set A universally Baire. So formally, we say we take a pair of trees, S and T, and we say they're absolutely complementing, or Z absolutely complementing for some set Z, if they remain complements of each other in every generic extension of the universe, collapsing Z in this case. Yeah, and we say the set A of reals is universally Baire if for every Z we find such a pair of Z absolutely complementing trees such that A is given by the projection of one of them. Okay, so that's the concept of a universally Baire set. Why do we care about it? Well, I mean, there are many applications of universally Baire sets. I mean, I want to focus on the ones in inner model theory. Yeah, because, I mean, this is a notion from topology. Yeah. And you can say, okay, maybe you can use an abstract set theory. I mean, you talk about trees. I mean, why do we care about them? Yeah. And it turns out that, I mean, they're not just like on the side, they're actually in the center of inner model theory. And the reason is sort of the following. So, I mean, this will be a very rough outline, yeah, and very vague, but let me just give you the idea. Because, I mean, I promise I don't want to talk about hot mice, and now I sort of have to break my promise partially, yeah? But I will do it in a way that is non-technical, yeah? Just to give you a motivation for the things that we do. Okay, so in inner model theory, what we want to do is we want to study canonical objects, canonical models that we call mice, and their strategies, yeah, their iteration strategies. Because for these objects, it's sort of important that we can iterate them, we can build alpha powers, and instead of just doing these linear iterations, we build trees, and we need strategies for these kind of trees. Okay, so the complexity of the model in terms of the large cardinals it can carry determines the complexity of the iteration strategy. Okay, if we start with the simplest model, which is just L, there's no, I mean, the strategy just means the model is well-founded. That's very simple in descriptive set theoretic terms. If the model only has measurable cardinals, for example, it's still like tractable. If some wooden cardinals comes into play, it's getting more complicated, and if, like, depending on how complex the pattern is of the large cardinals you want to put in the model, the strategy to iterate the model will be more complicated. Yeah. So for the model, the complication comes from the large cardinals. For the strategy, it's really like complication in descriptive set theoretic terms. But so what we really want to do is, I mean, we want to get these iteration strategies that sort of work for arbitrarily long trees. Yeah, and that's very difficult. Yeah, it means that we have trees of height omega-1 of even larger, and we want to find canonical branches to them. So we need to have sort of a strategy or a method of finding these branches. And one thing that makes everything much simpler is if we find iteration strategies where the uncountable part can be determined from the countable one. Yeah, so what we really care about is, I mean, countable object is sort of simple. Yeah, I mean, they're reals, sets of reals. I mean, this is something we can sort of measure with descriptive set theoretic complexity. So, I mean, in some sense, the countable part is simpler than the uncountable one. What we want is we want to have strategies where we automatically, if we know the countable part, we get the rest for free. Yeah, that would be really nice. And this is what the universally Baire-ness does for us. Yeah, so universally Baire iteration strategies. So when we code them as a set of reals, if they have the property that they're universally Baire, then they do this for free. Yeah? We get this automatically. Because universal, I mean, this takes a short argument, but universal Baire-ness, as I said, allows us to canonically extend to generic extensions. So if we have a very large tree, we can sort of collapse its size, make it countable, and look at the extension of the universally Baire strategy for countable trees to that generic extension. Yeah, that's the idea. So this is why universally Baire strategies are somehow magic. Yeah, if we understand them in the bottom part, then we understand everything. That's very nice. Yeah, I mean, it's a bit like moving from finite to infinite. Yeah, I mean, we're moving from countable to everything. Yeah, that's a real magic strategy. Yeah, and we care about these kind of strategies. And to understand what's going on, sort of, I mean, how they are helpful and what we know about them, I will talk about generic absoluteness. Yeah, but so in some sense, understanding these strategies just means that, yeah, I mean, how many? I mean, yeah, can we get the strategies? Yeah, is sort of the question. Okay, so generic absoluteness also starts from a very simple set theoretic fact. It's actually just based on Schoenfield's absoluteness theorem. Yeah, I mean, Schoenfield's absoluteness theorem implies that sigma-1 true truth just cannot be changed by forcing. I mean, it's even more general. I mean, it works for any large enough model. Well, very simple question. Can we extend this absoluteness theorem to the theory of canonical models of determinacy? Yeah, or to like more complex notions of definabilities and sigma-1 too. So there are like two results. I mean, the first one due to steel and wooden independently, the second one due to wooden, that tell us in some sense, yes, I mean, if there are some large cardinals around. Yeah, so suppose there's a proper class of wooden cardinals. I mean, I will not define what they are because we don't really need the definition. If you don't know, then just assume like some large cardinal hypothesis. And let's take two generic extensions. I mean, let's take V of G, so canonical expansion of the universe, and V of G star H, a further expansion. Then actually, I mean, you can prove that L of R, so just constructing over the reals, is a canonical model of determinacy. It's a model of AD, and you get an elementary embedding between the L of R versions of the generic extensions. Yeah, so the theory of L of R is somewhat absolute. And you can expand it, and you can plug in a universally Baire set if you want. So if you take an arbitrary universally Baire set, then you can still prove that L of A together is the reals. Yeah, so now we can use the universally Baire set as addition. It's still a model of determinacy, and there's an elementary embedding between the versions of this model in V of G and V of G star H. And I mean, the key is here that, I mean, since this is universally Baire set, we know what it should move to. Yeah, if we have a universally Baire set in V of G, then there's a canonical version for this in the further generic extension. Yeah, so we essentially know what this embedding has to be, because we know where to move the universally Baire set. Okay, so I mean, if you can plug in one universally Baire set, you can plug in two. The question is, can we plug in all of them? Yeah, okay, let's just do that. Yeah, let's look at the collection of all universally Baire set. So I mean, as before, we read the reals of G for the reals in V of G, and we set gamma infinity G to be the set of all universally Baire sets in V of G. Yeah, it's the set of all of these A's that are universally Baire. Is this a model of determinacy? Yeah, this was the first condition in the previous theorem. Is it a strong model of determinacy? Yeah, I mean, if yes, maybe it satisfies even more. Maybe it satisfies ADR, satisfies ADR plus theta is regular. Is there a generic absoluteness theorem for this model? Yeah, can we prove exactly the same things that we proved in the previous theorem, but for this model where we just, instead of one, put all the universally Baire sets? And you know, I mean, I don't know how you feel, but I mean, when I saw this for the first time, I thought this must be obvious. Yeah, because it just, I mean, you know, sometimes in math, when you prove theorems, I mean, you prove something for the simple case, you prove the one extension, oh, then you do the next extension. Yeah, I mean, it just goes very smoothly. But there's something more interesting happening here. Yeah. So if we put the questions that I had on the previous slide into a definition, we get what Wooden calls sealing. Yeah. So sealing is the conjunction of the following statements. First of all, for every generic extension, this canonical model where we put all the universally Baire sets, it's a model of AD. I mean, a little bit more, it's a model of AD plus. And we have a closure property, so there are no new sets of reals. I mean, all the sets of reals here are the universally Baire sets. I mean, this is somehow related to the question if this is a model of ADR, for example, yeah? And we have a generic absoluteness theorem. Yeah, this is what the second condition says. If we take a further generic extension, H, then we get this elementary embedding from this model to this one. And again, we know what the elementary embedding has to be, because, well, I mean, if we take a universally Baire set here, then we know we should move it to its canonical expansion in the further extension. Yeah, I mean, there's not much choice. I mean, if you want to extend the theorem on the previous slide, this is how it has to look like. Yeah, that's the most canonical thing to conjecture. So, I mean, simple question, is this true or not? Yeah, is this a theorem? What happens? Well, I mean, there's a theorem about it. That's Wooden's stealing theorem. So if there's a super compact cardinal, I mean, just be careful now, we made a giant jump in consistency strength there. Yeah? But if there's a super compact cardinal and we collapse it, we collapse even more, we collapse 2 to the kappa, and there's a proper class of Wooden cardinals, then sealing holds in the generic extension. Okay, but I mean, as I said, this is a giant jump in consistency strength. It's also like a different kind of theorem than the previous ones, yeah, because we get sealing in the generic extension. And I mean, sealing is actually not as nice and natural as you might think from the previous theorems, because it is connected to the inner model problem or the inner model theory in general. And it even, I mean, you could say it has a dramatic effect on the inner model problem. And I mean, let me just give you again a vague explanation why this is the case, or why we should care about this statement. Yeah? So all known canonical inner models, like all these mice that I sort of talked about, they have a canonical well-ordering of the reals. in this model. Well, but if you think about it, this contradicts the first clause of sealing already. I mean, we're not even speaking about generic absoluteness, just talking about the fact that it's a model of determinacy. Because models of determinacy don't have omega-1 sequences of their reals. Yeah? So what this tells us directly is that sealing cannot hold in canonical mice, at least not in the ones we know. Yeah? So if sealing is true, yeah, just outright, from some large cardinal, it means that there's no canonical inner model of the way we know it of this type of large cardinal. And now comes the warning. So Grieger, Sargsyan, and Nam-Trang proved that sealing is actually consistent from a wooden limit of wooden cardinals. Yeah? So the large cardinal strength of sealing is not as high as in this theorem. Yeah, I mean, they didn't prove it directly, but they proved, we should be a little bit careful when dealing with wooden limits of wooden cardinals, because these obstacles come up, and actually, I mean, there are more precise inner model theoretic reasons why we should be careful here. Yeah? But in the end, I mean, the question remains, like, is there a large cardinal that satisfies sealing directly? Yeah, that we don't know. Okay, so instead of answering this question, let's move beyond. Huh? I mean, if we can get a sealing theorem for all the universally Baire sets, what's the next step? So repeating the question from the first slide, the motivation, yeah? What sort of generically absolute subsets of the universally Baire sets can we add to this model? Yeah, I mean, now we sort of understand this model. Yeah, I mean, we put all the universally Baire sets and the reals. Can we do more? Yeah, can we add more sets and still get the same theorem? I mean, presumably now just by collapsing some supercompact cardinal a bit more, yeah? And I mean, let me just give you sort of a vague explanation why we care about this. So this is related to the study of like canonical mice in inner model theory again. So I mean, if we have some set X, say, I mean, we look at canonical operators like X sharp, M1 sharp of X, and so forth. And what we actually would like to do is we would like to look at like all of them in some sense, yeah, just like all of the universally Baire sets. Let's look at all of the operators that we can get from mice. And what we would like to do is, I mean, sometimes this is written as LP, like the lower part stack. We would like to add all of them to these kind of models, yeah. And okay, so from some inner model theoretic hypothesis, I mean, I would say in the presence of mouse capturing, if we look at this canonical embedding, yeah, I mean, this is like the embedding that you would get from a sealing theorem. You can look at the stack of all of these mice as just like stacking them. And I mean, this is sort of the complexity of the strategy that you're allowed to use. Yeah? We can use all of the universally Baire sets. And I mean, since we're doing it here, we have to move to the pointwise image. Yeah? And this idea motivates the definition of this UB power set. Yeah. So what we want to do is we want to sort of find a notion that morally captures all of these operators. And we would like to add all of these things to this model and then still prove that we have determinacy, a sealing theorem, and so forth. So that's the definition of the UB power set. Yeah? Let me do this a bit more formally. Okay. So let's take some set X. Yeah, and I mean, maybe just, I mean, I will go through it slowly. And let me just also emphasize that, I mean, there's no inner model theory in this definition, yeah? So there are no mice involved. Yeah, this is just a plainly descriptive set theoretic determinist theory definition. So we take some X, and I mean, let's take the maximum of the size of X and the size of the UB sets, because this is the amount we need to collapse, make things countable. Then we say the universally Baire power set of X is the set of all Y such that if we move to this generic extension, Y is ordinally definable in this model. Yeah, so we take subsets of gamma infinity in this model that are ordinally definable from these parameters. Yeah, and this is the thing that you saw on the previous slide. Yeah? This is very canonical if you think about inner model theory, but I mean, you don't have to think about it this way. I mean, you can just take this as your definition. The idea is essentially, I mean, if we go to the generic extension, then this is a countable set of parameters. Yeah? We collapse gamma infinity to be countable. This is just the pointwise image. So we take countably many parameters, and use them to ordinal define this set Y. Yeah, and this J is just the canonical embedding as before. You should just think of this as the embedding coming from ceiling. And more precisely, I mean, if you just assume that we have ceiling, then instead of just going to this one particular generic extension, you can just go to any generic extension that sort of captures that, that's strong enough such that it contains a generic collapsing this much. So what we do is, I mean, just to repeat once more, I mean, we want to what we really want to have is just take the power set of the universally Baire sets. Yeah, I mean, you take the reals, then the UB sets are somehow a canonical fragment of its power set. And now we want to have a canonical fragment of the power set of the power set of the reals. And the way we do it is this. Yeah, so the canonical fragment of the power set of the reals, I mean, in this case, the power set of the UB sets, yeah, it's just the ones that are ordinal definable from these parameters. Now that's our sort of conjecture for the I mean, just as the universally Baire sets are canonical fragment of the power set of the reals, this is a canonical fragment of the power set of the reals. Just going up to the next level. Okay, so now, I mean, ordinal definable in here, but I mean, remember, I mean, you should think of this under ceiling, yeah? So it doesn't matter if you do ordinal definable here or in a further generic extension. So this is sort of the uniformity that you get. I mean, the ordinals can change, but, you know, I mean, you're just moving the definition with the ceiling embedding. That's the idea. Yeah. And okay, so what can we prove about this model? So first of all, I mean, let me just write A infinity for the canonical power set. I mean, maybe that's not an excellent choice of notation, but I mean, I just want to write something shorter. So I mean, we write this for the UB power set of gamma infinity, and just like, let's just write A infinity to make it a bit shorter. So I mean, A infinity sub H is the UB power set of gamma infinity in this generic extension V of H. And so the first thing is we get that this is a model of determinacy. I mean, again, under appropriate large cardinals. So suppose that we have a supercompact cardinal, and there is a proper class of inaccessible limits of wooden cardinals. And let's take one of these lambda, and suppose we collapse or Levi collapse lambda. So I mean, this is just collapsing a bit more than you would have to do for the general ceiling theorem anyway. But under this hypothesis, ceiling holds in the model. So the UB power set really makes sense. There we get a canonical definition, and then we get a derived model theorem for it. So this is a model of AD plus. And yeah, I even wrote it. So I mean, I will say a little bit more about the proof in a minute, just like the idea here, for those who know. Okay, I mean, of course, we want to use ceiling. Yeah, I mean, without ceiling, the definition is not very, very stable. Yeah, but we suppose ceiling for everything, and then it's essentially a copy of Steele's stationary tower free proof of Wooden's derived model theorem, in case you know what these things are. Okay, so then the next step, I mean, now we know it's a model of determinacy. What we really wanted to have is generic absoluteness. So can we get a ceiling theorem for this? And the answer is again, yes, at least almost, or in depending on the way you think about the ceiling theorem. So we get a weak ceiling theorem for the UB power set in the sense that the models are always elementarily equivalent. So let me just state the theorem, state the statement first. So again, let A infinity be the UB power set of the universally Baire sets. And I mean, we write this for the ceiling embedding. I mean, if ceiling holds this canonical embedding between all the UB sets and the reals in V of G and in V of G star G prime for further generic extension. And we say that weak ceiling holds. Well, if first of all, a weak ceiling for this particular UB power set, if first of all ceiling holds, this is a model of AD plus. So these two things we know already. Yeah, I mean, if we in some large generic extension, collapsing is a bit more than a supercompact. I mean, by Wooden's sealing theorem, sealing holds. And by the theorem from the previous slide, we know that this is a model of determinacy. I mean, even a model of AD+. Yeah. I mean, the difference between AD and AD+ is not very relevant here, yeah? For those of you who don't know AD+. I mean, you can say you get the plus for free from Steele's proof, yeah? Okay, so I mean, but these two things we have already. And the next thing is the real sealing part, yeah, the generic absoluteness. When we say, okay, whenever we take two consecutive generics, and now we need to assume a little bit more. I mean, I don't want to take two arbitrary consecutive generics. I want to make sure that the second one collapses enough of the first one. Yeah, so this is a small additional assumption. I mean, instead of taking two arbitrary ones, I assume that in V of G star G prime, 2 to the omega of V of G is collapsed. Yeah, so just we go a little bit more. You know, but I mean, whenever you have a G, you can just like go to, you know, you just need to make sure that you go far away, like a little bit further. And then we get an elementary embedding between these two canonical models that actually just extends the one from sealing. Yeah, so this is the generic absoluteness theorem for these models. In particular, this implies that the theory of the UB power set of the universally Baire sets cannot be changed by forcing. Yeah. Okay. And then, so this is just the definition again. Now the theorem. So if you take a supercompact cardinal, and again, there's a proper class of inaccessible limits of Wooden cardinals, and you collapse 2 to the kappa. Again, so this is almost the same hypothesis as for Wooden's sealing theorem. Then weak sealing holds for the UB power set in V of G. Yeah. Okay, so now you might wonder how to prove this. And well, I mean, there's not enough time to go through all the details of the proof, but I want to give you a rough idea, yeah, of what's happening behind it. And there's one key technical lemma, and it turns out, I mean, the way this started was sort of that we started trying to find a new proof of Wooden's sealing theorem, and then we realized that we can use the same proof to prove even stronger results. Yeah. So the idea behind the proof of the sealing theorem is that we want to get rid of the stationary tower forcing. So in case you know, I mean, the original proof of Wooden's sealing theorem is using this machinery stationary tower forcing. And what the key technical lemma gives you, I mean, not directly, but like almost immediately, is that you can prove it without stationary tower forcing. Okay, let me put the lemma, and I will go through it slowly, okay? So what we get is a derived model representation of the universally, I mean, this model with the universally Baire sets at the reals. So, I mean, maybe just a few words for those who don't know what this is. I mean, I used the word derived model theorem a couple of times. What the derived model theorem does is that it gives you canonical models of determinacy. I mean, it's like the canonical way of proving that something is a model of determinacy. Yeah, and the models of determinacy that come out from the derived model theorem always look like this. Yeah, it's L of Hom star R star. So you do some Levy collapse and you look at the things that are homogeneously Suslin and the reals that are appearing along the way, roughly. Yeah, so, and the derived model theorem gives you that this is a model of determinacy. And sort of instead of proving that the thing we have is a model of determinacy directly, we prove that it's a derived model. Yeah, so I mean, we really care about this model. And the way we prove, for example, that this is a model of determinacy is that we prove that it's of this form. And then we can just sort of use the derived model theorem for this model. And the derived model theorem, or this model, is even nicer because it does not only give us semi-automatically that this is a model of determinacy, it also gives us that this is a model of sealing. I mean, there's a pretty generic argument, yeah, that allows you to derive from this derived model representation that this is a model of sealing. And okay, so let me just now go through the statement of the theorem or technical lemma. So what we do is, so let's take a supercompact cardinal and suppose there's a proper class of Wooden cardinals. So always sort of the similar setting. Okay, let's collapse 2 to the kappa, and let's collapse sort of 2 to the omega of that model in the next step. Then there's an elementary embedding from V to M. Okay, we even know where the supercompact cardinal moves. It's going to be omega 1 of M of G star H. And this model that we care about, yeah, the universally Baire sets of V of G star H and the reals of V of G star H, is a derived model of this iterate. Actually, yeah, I mean, I didn't state it here, but I mean, you can get this as an iteration embedding, yeah. It's an iterate M, and then you can get this as a derived model of M. So, I mean, what it means to be a derived model, as I said, is just that if you take some generic G Levi collapsing omega 1, in this case, you get that this model is just equal to this one. And I mean, in fact, I mean, for proving the statement about the UB power set, we use a slightly more general version of this, because I mean, the nice thing about this is actually, I mean, it's not really the statement, it's the proof that's really nice, yeah? The proof is what we care about, but it's hard to put on one slide. But I mean, the idea is that we can get this elementary embedding here, as I said, from an iteration, and we can even set it up in a way that sort of, we not only get this derived model representation here, but we can like get derived model representation passing through certain universally Baire sets. I mean, the way of setting this up is very flexible. Yeah, we sort of have a lot of flexibility of arranging the iteration in a way such that, I mean, first we do some iteration and then we catch, for example, gamma infinity G star H, and then we do it further, we catch gamma infinity G star H star some H prime, and so forth. And the way this is set up allows us to prove also the derived model theorem plus the ceiling theorem for these definable power sets, for example. Okay, so I mean, instead of dwelling at the proof, because actually, I mean, for those of you who are interested, there's a preprint of this on the archive already that I can also email you. And okay, maybe I should just like make one comment. I mean, that also contains another application. I mean, we have the application for the UB power sets, and there's an application about adding supercompactness measures to the model. So that you can all find online. I mean, let me close the talk by moving even beyond and make some conjectures, yeah, how to extend this even further. I mean, I said eventually, I mean, I think it would be super nice to get models as strong as like the Larsen-Sargsyan model, where you can actually force the failure of the KC iterability conjecture over it. But for that, we need to go, I mean, we need to do much more, yeah? And I mean, one way to extend this model is, for example, inspired by considering Chang models, yeah? I mean, what I say here is not very precise, yeah, but let me just start by giving you the vague idea. I mean, now we have our model L, where we put not only the reals, not only all the UB sets, not only all the definable power set of the UB sets, we also put countable sequences. Yeah, I mean, this is just like going beyond. I mean, as I said, we take the reals. I mean, we take canonical power set of the reals. This is the UB set. We take a canonical power set of the reals, which is the UB power set. I mean, let's see what we can do more. Yeah, what can we add to the model and still get, for example, determinacy, a ceiling theorem, and so forth. And one idea is, okay, let's suppose that we also add countable sequences. So we get a chunk type model. Well, I mean, so to get that this really is an extension, we should argue, for example, that this has cov omega, in the sense that, I mean, this is really more. Yeah, if this, like the formal version of this is cofinality omega, then there are some omega sequences that are missing. So this is really an improvement of the previous theorem. Yeah, so this is just something to keep in mind. I mean, formally, what we should do is, I mean, let theta x be the supremum of all ordinals such that there's an ODX sujection from the reals onto alpha. And this is just, I mean, if you cross out the theta, the x, sorry, this is just the definition of theta, and we relativize it to x. Then let eta infinity be the theta of the UB sets of our favorite model, gamma infinity R. And then, I mean, the model I said here, you should read it. This, I mean, let's just add all the countable sequences of this thing. together to A infinity, then the conjecture would be that this is a canonical model. Again, in the sense that, okay, if you suppose you collapse some large cardinal above a supercompact, then, I mean, first of all, the cofinality of this should be omega. So you actually add something, plus you do get a ceiling theorem for these kind of models. Yeah, but this is a conjecture, not a theorem. Okay, thank you. You can ask questions about it.
Yes. Any questions? Yeah.
You said you put in UB powerset as nice overview. Can you show that nice overview?
Yes, I mean the idea should be, or maybe now I can use the thing here. Okay, so the idea should be, I mean, if you work in a hot mouse, for example, yeah, or like under some mouse head conjecture, the UB power set, let's say of gamma infinity should be just LP sigma over gamma infinity, where sigma is just the join of all the strategies that are co-final in so sigma alpha, where these are, oh, sorry, we'll probably not be able to read it if I write so low. So these are just strategies co-final in gamma infinity. Oh. Yeah, I mean, you were asking about this, yeah? But I think you can actually get equality. I have no idea. You were asking what sentences are in the theory of. I mean, we know that the. Oh yeah, that's true. Yes, ADR plus theta is regular.
It looks like for this one you could get Solovay levels.
But only for this one, not for the.
Well, I mean, you could show this proof. If the conjecture is true, you could prove that that L gamma infinity. Not that there is a model, but there is actual.
Maybe at the next Gdansk logic conference. I think it's your turn to ask Obret.
So you at some point you use, or more than one point, you use something like this ceiling embedding, that terminology. Well, I guess it's easy to me, or I mean, if it has, does it have a critical point? That's my question. And if it does, then I guess it's not unique. So.
I mean, so there's in some sense only one embedding that you can consider, because let me just write down the embedding. Okay, because, so let me just repeat. I mean, you want to get an embedding from L of gamma infinity R to L of gamma infinity G. RG. Okay, and so, I mean, we can suppose that the sharp of this exists. And then, I mean, this embedding is just given by, I mean, taking some term in L of gamma infinity R, and, I mean, take a real, a UB set, and some indiscernibles. Yeah, we call them, I don't know, S. Yeah, so this is a real, this is a UB set, and this is a finite sequence of indiscernibles. Well, I mean, so this is how all the objects in here look like, yeah? If you have this is a sharp. Well, I mean, if you now want to compute J of this thing, you know what to do, yeah? There's only one option, because this has to be, okay, you take the same term, now you interpret it in this model. And, well, the real doesn't move. Yeah, so it's the same real. The UB set A should move to its canonical interpretation. And you take indiscernibles, yeah? I mean, all the reals are the same, but beyond that, you have no idea, yeah? Mm-hmm. Yes. Yeah, but I mean, I think this is really the best. I mean, you know, I'm not sure if thinking about, I mean, this is not an embedding where you should think about its critical point, because this is sort of not capturing the structure. I mean, it's just an ordinal, right? I mean, what we really care about is like how these sets of reals move, for example. So, I mean, theta is the much better question than, yeah. Mm-hmm. Mm-hmm. Yes. Yeah, I mean, it's just like, I mean, okay, it's not on this slide, but it was like on one of the previous ones. I mean, when you think about the UB power set, I mean, the pointwise image of gamma infinity here will be usually countable. Yeah, I mean, this is a generic extension. You can collapse all the UB sets to be countable. In most cases, you will, yeah? This is the more interesting case. Mm-hmm. Yes, but actually, I mean, the reason why, I mean, sort of the fact that this is the only embedding you can consider is heavily used in the proof of these things, yeah? Because we know the embedding, so you just need to prove that it's elementary. And using this derived model representation, you can sort of put like the model here, go back to V, and go forth again to the other model. Yeah, this is the idea.
One question from online, but I don't.
Should I come and read the question? Does it help?
Takehito, can you hear us? Can you ask a question? Hey, because yes, please. Yes, you can ask your question. We'll hear you. Please try. We cannot hear you. Can you turn on your microphone? I'm speaking, but I can't hear you. I can't unmute, but you are unmuted already. How about now?
Hi, can you hear me?
Oh, very good. Yes, Takiko, now we can hear you.
Okay.
Let me just run back to the others.
Yeah. Thank you, Sandra. I have one question. Can we say something about sets of reals in LA infinity through your Soling proof or something else?
Okay, let me just think about the question once. So sets of reals. I mean that. I mean, not really. I mean, okay, we know something about the sets of reals by the, yeah, sort of the ceiling thing, but sets of reals.
So the reason why LA infinity satisfies 80 plus just because the set of reals is just gamma infinity. So, right? It doesn't increase any set of reals.
Yes.
I see. But
I mean,
we don't even know that if there is another sets of reals other than A infinity, I guess. So okay, so the answer is the proof doesn't tell us about sets of reals.
No, I mean, okay, so I mean, if you take I mean, the idea behind the definition of the A infinity is that it's all the ordinal definable sets of, I mean, subsets of gamma infinity. If the sets of reals, I mean, the sets of reals we have are the ones from gamma infinity. So instead of asking about sets of reals, you can ask about subsets of gamma infinity.
Yes.
But all the subsets of gamma infinity that appear are ordinal definable, so they are in A infinity again.
Oh, right. Yeah. Okay.
So that you can, yeah. I mean, that follows from the, I mean, that the definition is so general in some sense, yeah.
I see.
But yeah, I mean, what happens at the next level, I don't know, yeah.
Okay.
Or I mean, for example, I mean, that's another question also about like this Chang model type, yeah. I mean, you know that, I mean, you should try to prove that you actually add countable sequences, but then, I mean, you need to ask, okay, I mean, what actually do you add? I mean, analyze the model.
Thank you so much.
Sure.